Good morning, welcome to the next lecture on random processes. So far what we have done is we have defined a random process, we have looked at a special kind of a random process, that is a Gaussian process, we have defined jointly Gaussian random variables, we have defined random vectors, we have defined Gaussian random vectors, and today we would be continuing with random processes, and today we will cover two important concepts in random processes, that is the linear functional of a random process, and then we will look at what happens when a random process passes through an LTI system, a linear time invariant system. So, let us get started with linear functional. So, what is a linear functional? So, if you have a random process, remember that a random process is usually denoted with a capital letter, and it is a function of two independent variables, time and outcome of the experiment. So, let us assume that we have a random process z of t, and if I take the inner product of this random process with a deterministic function, that is the linear functional of a random process. So, linear functional of a random process is simple, linear functional of a random process is nothing but it is the inner product of the random process with some deterministic function g of t. Okay. So, you know how to calculate the inner product. So, for calculating inner product we have to evaluate this integration, and usually as you know that we have to take a conjugate in one of the function, but because g t is a real function we do not have to take this conjugate. So, the inner product of a random process with a deterministic function, if everything is real, can simply be calculated like this. So, this is the inner product of a random process with a function, okay, and this we say as the linear functional of a random process. Now, some important points here before we move on to another section is that is this inner product always defined? It need not be, and as we have seen from the vectors, this inner product is always defined if zt and gt are L2 functions. So, what we are assuming is gt is an L2 function, and what we are assuming is the sample function of this random process is also an L2 function, because if they are L2 function then this inner product is always defined and we do not have to worry then about the convergence issues and so on and so forth. So, to simplify, to not talk anything about the convergence, what we assume is the inner product is always defined because the sample function of the random process is an L2 function and gt is also an L2 function. So, let me write that inner product again. So, this is the inner product of the random process with a function g of t. Now, let us look what is this quantity, what do you believe this quantity to be? This quantity, if you see, will not be a function of t. Why is this not a function of t? Because t is the running variable. So, it will not be a function of t, but it would be a function of omega. So, what you would get is a real number, v of omega is a real number, and this number would depend upon omega. So, this v of omega is a random variable, is a random variable. So, what we see now is that a linear functional of a random process is nothing but it is a random variable. Why is this a random variable? Because it will only be a function of omega, it will not be a function of t. T is the running variable. You are having a definite integration which you are evaluating from minus infinity to plus infinity. Okay. So, we have looked into what is a linear functional of a random process. Now, let us see what happens if you have a random process and what happens if you pass this random process through an LTI system. Okay. So, if you have a random process and if you pass this random process through an LTI system, let us see we get some output. How to evaluate this output? So, you know that this output could be computed simply by convolution. So, I need to take the convolution of this random process with impulse response, and I have to integrate it from minus infinity to plus infinity. So, I have taken the convolution of a process with impulse response. Okay. This you must know already. Now, look at this, what this integration is a function of. It is not a function of tau for sure, because tau is a running variable. It is a function of both t and omega. So, we have got y of t and omega, it is a function of t and it is a function of omega. So, what you end up with is a random process. Okay. So, the output of an LTI system, if you pass a random process through an LTI system, what you get is a random process. Okay. So, let us summarize what have we said so far. So, what we have said is a linear functional of a random process is nothing but it is the inner product of the random process with a deterministic function. That is one thing that we have studied. The second important thing is, if you pass a random process through an LTI system, what you get is a random process itself given by this expression. Okay. Now, let us see these things for special kind of a random process. That is the Gaussian process. We love Gaussian process because it is easy to evaluate linear functional and output of a Gaussian process, and moreover it is also very practical, right. So, Gaussian process is easy as well as practical. So, let us take an example of a Gaussian process, and we know that I can generate a Gaussian process through this orthogonal expansion function. So, I can consider a random process which is expressed in terms of orthogonal functions, and the coefficients of these orthogonal functions are nothing but 0 mean, independent, Gaussian random variables. Okay. So, if you use this framework can be used to model all interesting Gaussian processes. It cannot model all Gaussian processes, but it can model all interesting Gaussian processes, the Gaussian processes which are of interest to us. So, let us revisit why can this generate a Gaussian process. So, let us take a sample of that process. Okay. And we have also said that most of the time we would take these orthogonal functions to be t spaced sinc functions. Okay. So, let us now specify what these orthogonal functions are. So, the random process then can be written like this, and if we assume a particular instance of t, that is t1, what I get is this expression. Now, as you can see, what you get is a linear combination of independent Gaussian random variables. A linear combination of independent Gaussian random variables is nothing but a Gaussian random variable. So, ZT1 is a Gaussian random variable, and if you take a second sample, another sample of this process, what you get is this expression. So, what has changed? Nothing has changed. So, we are putting a specific value of t. So, in this case we have put t as t1, in this case we have used t as t2. Now, what you get again is you are getting a linear combination of independent Gaussian random variables. So, ZT2 is also a Gaussian random variable, and what more, they are different linear combinations of the common underlying set of independent Gaussian random variables. So, ZT1 and ZT2 are also jointly Gaussian. So, they are also jointly Gaussian random variables, and if the samples of a random process are jointly Gaussian random variables, then the process is a Gaussian process. So, what I have convinced you again, because it is so important that this process can be used to create and model Gaussian processes which are of interest to us. Okay. So, let us assume that we have taken such a Gaussian process, and let us see what is the linear functional of such a process. So, linear functional is defined as the inner product. So, I have to take the inner product with, let us say, a deterministic function g t. Okay. Now, pulling out this summation, bringing in the integration as we usually do, I can write this as okay. Now, what we can see from there is that this function is it a function of time? No, it is not a function of t, because we have the running variable as t, it is a function of k, right. So, I can write this as, we are not interested in what is the value, but rather I can say that this is some function g k. Okay. So, it is a function of what is your g t, and it is a function of k. Now, g k is a real number, right. Say it is some real number depending on the value of k. So, what you end up with is a linear combination of independent Gaussian random variables, and we have seen that a linear combination of independent Gaussian random variables leads to a Gaussian random variable. So, V omega is a Gaussian random variable. So, what we have learned is a linear functional of a Gaussian process is a Gaussian random variable. Let us take a linear functional, let me write this as V1 omega for some other deterministic function for the same Gaussian process. Let me take it for f of t dt. So, now I have replaced g of t with f of t is another deterministic function. So, similarly you can show that this would be nothing but, using the same analogy, we get that V1 omega is again a linear combination of independent Gaussian random variables, where value f k is decided with the k and what function you have assumed. Now, if you see that V1 omega and V omega they are the different linear combinations of the common underlying set of independent Gaussian random variables, and thus these are jointly Gaussian random variables. Why are we studying all this? Is because most of the time what you deal with is how does a random process interacts with the digital communication systems, with your receivers and so on and so forth, and in that context understanding about linear functional will be going to help us a lot, and thus this idea of linear functional is important. Now, let us see what happens when a Gaussian process passes through an LTI system. So, let me assume that we have an LTI system, and let me assume that the impulse response of this LTI system is h of t, and let me assume that at the input of this LTI system we have a Gaussian process. Okay. And as you would have known by now that zk, for this to be a Gaussian process, the zk has to be independent Gaussian random variables. So, let us ask the question, what is this yt? So, first we know that it should be a random process itself, and this should be summation k zk sinc tau by t minus k into h of t minus tau t tau. Okay. Then pulling the summation out, putting integration in, what we get is zk okay. Now, from this what we can write, if you see this carefully, now what is this? This is a function. So, we are not interested, as before we are not interested in what this integration evaluates to, but we are more interested in what is this quantity. So, if you see that, let me first write and then explain. So, we would have zk, and this quantity would be a function. Now, it is a function of t, okay. It is a function of t, and this is also a function of k. So, what we would have is, let us say we would have hk t, because it is a function of time. Now, this is a random process because it is a function of time. Now, if you take the sample of this process at, let us say, specific time instance t1, what we get is zk hk t1. If you take the sample of this process at a time t2, what we get is zk hk t2, right, just substituting t as t1 and t2, and what you see now is, what is this again? Now, this is some numbers, some coefficients. So, again yt1 is a linear combination of independent Gaussian random variables. So, yt1 is a Gaussian random variable, and yt2 again it is a linear combination of independent Gaussian random variables. So, yt2 is also a Gaussian random variable. What more is, again they are different linear combinations of common underlying set of independent Gaussian random variables. So, yt1 and yt2 are jointly Gaussian random variables. So, everything is very similar to the last time. So, they are also jointly Gaussian random variables. So, what we can say now is yt is also a Gaussian process, right. Similarly, you can do it for any samples, and you would see that the random variable created by looking at this process at a specific time instance would nothing but it would be different linear combinations of the common underlying set of independent Gaussian random variables, and thus you can say every sample created by looking at this specific by looking at this process will be a jointly Gaussian random variables, and hence you can conclude from this is yt omega is a Gaussian process. That is a very important and useful observation, that if you have an LTI system, linear time invariant system, if you have a Gaussian process at the input of this LTI system, the output process is also Gaussian. So, if input is a Gaussian process, output is also Gaussian process, and we say this by saying that linearity preserves Gaussianity, right. So, this can be any linear system, linear time invariant system. So, if you have a linear time invariant system, what happens is input is Gaussian process, output is also Gaussian process. So, very useful result. Okay. Now, let us define different types of random processes. Let us define different types of random processes. And the first interesting class of random process is a stationary random processes. What is a stationary random process? Let us try to first understand it intuitively. So, suppose if you have a random process z of t, and if you delay this random process by some amount, let us say if I delay this with d units, right, then these processes z t or z of t minus d are statistically indistinguishable. Okay. That means you take a random process, you delay it by any time units you want, then the process that you create is statistically indistinguishable from the original process. If that is the case, then the random process involved is known as a stationary random process. That means it does not care where your time origin is, right, does not care what is your value of t. Okay. So, such processes are known as stationary random processes. So, let us see mathematically how can we define this more concretely, but before taking that mathematical definition, let me warn you, do not think, suppose I have a random process which is a collection of several sample functions. So, let us look this process at time instance t, and let me look this process at time instance t plus d. Okay. So, I am looking this process at two different time instances. What I am saying is, if this process is stationary, then statistically this sample is same as this sample. Statistically, it does not mean that this value is same as this value, I do not mean that, right. So, you have to really understand what stationary random processes, do not get confused that the sample functions are completely deterministic, they are not, right. Statistically, if you see this random process at a time instance t or at a time instance t plus t, the statistically these samples are same, that means they have the same mean, they have the same probability density function and so on and so forth. Okay. So, that is the meaning of statistically indistinguishable. Let us try to see how can we define mathematically stationarity. So, suppose I have a random process. So, let me draw this so that you get a grip of what is a random process, and I sample this at different time instances. Now, when I sample a random process at different time instances, what I am going to get? I am going to get certain random variables, and if I get certain random variables, I can define what is known as the joint CDF, right. So, let me define the joint CDF. Okay. So, this is how we define a joint CDF of this random process. Now, you know what is a joint CDF? It is saying that what is the probability that random variable x t 1 takes an argument less than or equals to x 1, and random variable x t 2 takes in a value less than or equals to x 2, and so on and so forth. Random variable x t l takes in a value less than or equals to x l. So, we have already discussed what a joint CDF is, just we can define a joint CDF for this random process. Now, if this random process is a stationary random process, what should happen more is that if you delay these samples by let us say some d times, so instead of t 1 you collect the random variable at t 1 plus t. Similarly, then if a process is stationary, the joint CDF that you obtain by sampling the process at time instance t1, t2 and so on and so forth up to TL is the same joint CDF if you sample the process at time instance t1 plus d, t2 plus d and so on and so forth up to TL plus d, of course for all epochs x1, x2, xl and for all values of d, right. So, if this equation is satisfied, then we say that the process is a stationary process. Okay. So, as you can now see that stationarity, checking stationarity is also very difficult, right. It is not easy to prove that a joint CDF of L random variables involved does not change when you shift the sampling time by d units, okay. And you have to do it for all values of L, right. 1 or 2 would not be sufficient, you have to do it for all possible positive integers. So, doing this would be difficult. Now, let us see some interpretations of what stationarity can mean. So, stationary T will mean that, as we have already said, the insight is that if you shift a random process by d units, if you delay a random process, then this random process remains statistically indistinguishable, and we have also said that the process does not care where the time origin is. So, let us say that we have a covariance function. We have already defined what a covariance function is. So, let us assume that we have obtained a covariance function by sampling the process at time instance t1 and t2. Now, this covariance function should also be same as this covariance function. That means, if you shift the t1 by d units and t2 by d units, then you should get the same covariance function, because the process is stationary. This is not always true. This is only true when the involved process is a stationary random process. That means, the sampling or random process does not care what the absolute values of time instances are, right. So, it does not care whether you have t1 and t2 or you have t1 plus d and t2 plus d. Okay. Now, I can choose any value of d. This must be true for all values of d. So, let us choose d as minus t2. So, if you choose d as minus t2, what you get is kz t1 minus t2 and 0. Now, this is interesting. So, for a stationary process, the covariance function obtained by sampling the random process at time instance t1 and t2 is nothing but it is the covariance function where one time instance is t1 minus t2 and the other time instance is 0. Okay. Now, this 0 is kind of redundant. So, I can write this as kz t1 minus t2. Now, see what we have done. So, this covariance function is a function of 2 arguments, right, but this covariance function is a function of only one argument t1 minus t2. So, when you see the covariance functions with one argument, what you should interpret? You should interpret that this covariance function should be of a stationary process, right. So, whenever you see a covariance function of one argument, like in this case, it should hint to you that this is a covariance function of a stationary process, a stationary random process. Now, furthermore, what it would imply is that the argument here t1 minus t2 should be nothing but it should be the difference. So, how to relate this from this? So, this t1 minus t2 you should interpret that this should be nothing but it is the difference of 2 arguments in the case of the covariance functions with 2 arguments. For example, if I have k z tau and this is a covariance function of a single argument. So, you should interpret this as that this should be same thing as when if I am writing this in terms of 2 arguments, then what we should have is tau and 0. Okay. Okay. So, this is what stationarity leads to. Stationarity converts a covariance function which is normally with two arguments in the covariance function with single argument, where the single argument denotes the difference between the time instance of the covariance functions with two arguments. Okay. What should happen to the mean? So, normally mean, as we have illustrated before, so what is the mean of a random process? So, you sample this random process at a time instance t1, then the mean of the random process can be understood as the mean of this random variable xt1. xt1 is a random variable. So, you calculate the ensemble average of this random process, or you calculate the expected value of this random variable xt1, and similarly you can calculate the mean of this random process by varying your t from minus infinity to plus infinity. So, mean is generally a function of time, is not it? So, because at every time instance you get a random variable and then you calculate the expected value of that random variable, right. So, mean is a function of a time for ordinary random processes. But now if I am talking about the stationary random processes, and if I am saying stationary random processes does not care where the time origin is, then what it would mean is that mean should not be a function of time, it should be a constant, right. So, mean of a stationary random process should be a constant. That means you can choose any value of time. For example, I have chosen the time to be 0. So, mxt is nothing but mx0. In fact, you do not have to specify what the timing instance is, it would be independent of the time. So, mean of a stationary random process is a constant, right, it is not a function of time. Okay. So, what we have learned is that when we are talking about the stationary random process, things becomes even simpler, right. Simpler in the sense that the covariance function, which is normally is a function of two arguments, reduces down to a covariance function of a single argument, and the mean remains constant. So, these are some effects of a stationary random process. Now, let us define another class of random processes, which are known as White-sense stationary, in short WSS, White-sense stationary random processes. And what are they, right? So, of course, they are stationary random processes in some sense, in wide sense, right. So, what we say is a process, a random process is a White-sense stationary if the covariance function, two argument based covariance function, is nothing but, you can convert this into a single argument based covariance function, and the mean of a random process is a constant. Okay. So, these are the effects of the stationary process that we have already discussed. So, if this process is stationary, it needs to satisfy these two conditions, right. It needs to satisfy the two argument based covariance function can be reduced to a single argument based covariance function. This we have already proven, and what more, we say that the mean is constant, it is not a function of time anymore for a stationary random process. Now, so if these two conditions are satisfied, we call that process as a White-sense stationary process as well. Now, so you can imagine that every stationary process is a White-sense stationary process, right. But other way around is not true. If a process is White-sense stationary, that means these two conditions are satisfied. That does not mean that a strict condition of stationarity is satisfied. What is a strict condition of stationarity? A strict condition of stationarity is this. So, you have to prove a stationarity, you have to prove that this equation is satisfied for all epochs, for all arguments, for all values of d, right. So, this is the strict condition of stationarity, but these are kind of weak conditions, right. These are weak conditions that you can say that the process is a White-sense stationary process if only these two conditions are satisfied. Okay. So, every stationary process would satisfy these two conditions. So, every stationary process is a White-sense stationary process, but every White sense stationary process will not be stationary process. Okay. So, there is some confusions in case of the language used. Sometimes the white sense stationary process is also referred to as a stationary process, right. To avoid any confusion in the words, sometimes these stationary processes are also referred to as strictly stationary processes, and these white sense stationary processes are referred to as white sense stationary processes. It is also important to note that these words are not used consistently in literature. So, remember that when we say stationary or a strictly stationary process, we mean that joint probability density function of the random process is invariant to time shift, whereas when we say white sense stationary process, it simply means that covariance function and mean is invariant to time shift. So, normally as you can imagine, thinking about a stationary process is or a strictly stationary process is really difficult. So, we will stick to white sense stationary processes only, right. So, these white sense stationary processes are processes of practical importance, the one that can be easily defined and can be used. Okay. Now, let us take some example, right. So, let us take the good old example of the random process that we have been using so far. So, what does this produces? If it is a 0 mean independent Gaussian random variable, 0 mean is not important, but we are saying it because we have been defining them to be like this always, then you see that it produces a 0 mean Gaussian process, right. Now, we have already seen that what is the covariance function for such a process. If you remember, the covariance function for such a process can be calculated like this. We have already proven this. So, you refer to one of the classes in which we have calculated the covariance function of this random process, and what we observed then is that the covariance function evaluated at T1 and T2 is not depending upon the absolute values of T1 and T2, rather it was depending upon the difference of these timing instances, right. So, hence this process, this framework that we have been using can be used to model white sense stationary processes only. So, it models white sense stationary processes or white sense stationary random processes. That is one insight. So, together with modeling a Gaussian process, it only models Gaussian process that have white sense stationary Gaussian process. That is one thing. The second thing is, now we know that a Gaussian process is only characterized means when we are talking about its joint PDF. We already determined what is the joint PDF of a Gaussian process. There we saw that this is only characterized by its mean and covariance function. Now, if it is characterized by its mean and covariance function, and if the Gaussian process is white sense stationary, if Gaussian process is white sense stationary, that means its covariance function does not depend upon the absolute values of timing instances. That means this joint PDF also does not depend upon the absolute values of timing instances, because joint PDF is only a function of mean and covariance, right. So, let us say that if the process is white sense stationary, that means the mean is constant and covariance function does not depend on absolute values of time, right. And hence this joint PDF is also So, does not depend upon absolute values of time, and hence if a Gaussian process is White sense stationary, it means that it is also stationary. So, everything simplifies for a Gaussian process, right. So, we have said in general it is quite difficult to prove whether a process is stationary or not, because we have to write this joint PDF, but for a joint PDF in the case of a Gaussian process is easy, because it is completely characterized by its mean and covariance function. So, if we say that the process is White sense stationary, that means its mean is constant and this covariance function does not depend on absolute values of time. From this we can conclude that this joint PDF is also time invariant, it is not depending upon the absolute values of time, and hence the White sense stationary Gaussian process is also stationary. The two more points that we will like to point out at this point is, because we are mostly talking about zero mean processes, right. The covariance function, let us say the covariance function of two random variables, or the covariance function of a random process where you sample the random process at two timing instance, is nothing but it is the same thing as its autocorrelation function, right, because it is a zero mean. The difference between covariance and correlation only comes in terms of mean. If something is zero mean, then either you can talk in terms of the covariance function or you can talk in terms of the correlation function, it means one and the same thing, right. So, whatever we have said for the covariance function also remains true for the correlation function. So, for example, if I want to say about the White sense stationary process, I can say a White sense stationary process is a random process which has a covariance function which is time invariant, that means it does not depend upon the absolute values of time, right, and this boils down to T1 minus T2 using the same ideas as we have used for the covariance function. In short, if it is a zero mean process, whatever we set for covariance function can be set exactly for the correlation function, autocorrelation function. That is one point. Second point is, let us see, if the process is White sense stationary, or let us say stationary, that means we do not talk about the time origin, right. So, that means when you are defining this process, you have to define it from minus infinity to plus infinity, because it is not a function of time. So, in terms of the time, this process should exist from minus infinity to plus infinity, right. Now, if something exists from minus infinity to plus infinity, that thing is going to have infinite energy. Think more about this. So, anything that exists from minus infinity to plus infinity, if the sample function is a stationary, or if the random process is a stationary existing from minus infinity to plus infinity, then it must have infinite energy. Now, if it has infinite energy, all this L2 theory that we have developed does not work, because L2 theory is for the sample functions with finite energy, right. So, in order to get rid of this problem, sometimes you talk about the effective White sense stationary or effective stationary process, meaning that the process is not completely stationary, but it is stationary in the timing limits minus t naught to plus t naught. Okay. The process is stationary only within this time interval, and after that the process does not exist, it becomes 0 or whatsoever. Then if you consider the process to be effectively White sense stationary, it would have the finite energy, because this process exists only between minus t naught to plus t naught, right. So, any effective White sense stationary or effective stationary process would be a random process with finite energy, and all this L2 theory will work. And how do we choose this t naught and minus t naught? As long as they are pretty large, it does not matter, right. For example, how does this random process behaves in very far future, or how it behaved in the past before minus t naught, if t naught is pretty large, is not going to impact us today, right. So, these limits does not matter as long as the value of t naught that is chosen is pretty large. and what does this help us with is it makes the process with finite energy. So, this idea is also sometimes used, though we will not use it, but in certain textbooks you would find another class of Whitesands stationary and stationary process is known as effective stationary process. That means they are only stationary within a time window, right, and this time window is chosen to be pretty large, so that it does not impact the present. Okay. So, let us now define another process which is ergodic random process. So, what is an ergodic random process? A stationary process, a stationary random process is an ergodic random process if the statistical averages are same as the time averages. Okay. So, we have defined what is an ergodic random process. So, the sense is, first of all, it has to be a stationary random process. Okay. If it is a stationary random process and if its statistical averages are same as the time averages, we say that the process is an ergodic random process. Now, what are the statistical averages? So, statistical averages are the same as ensemble averages, or they are same thing as taking expectation, okay, taking expectation. So, these are one and the same thing, and the time averages are one that you have already studied, right. You have already studied how can you take in time average of a quantity. So, ergodic random processes, for an ergodic random processes these averages are same. So, we would choose to take an average which one is more convenient. Okay. So, it is an important class which we will talk about in the next lecture. So, what we have seen today, we have defined what are the linear functionals and we have got some insight into how does a random process behaves when it passes through an LTI system, and more or less we have defined various important classes of random processes. We have defined what is a stationary random process, we have defined what is a Whitesands stationary random process, and now we are going to define what is an ergodic random process. And remember that most useful random processes are Whitesands stationary random processes, and if a process is a Gaussian random process and if it is Whitesands stationary, that means it is also a stationary random process. We will see more of this in the next lecture. Thank you.